This lesson is entitled The Mean Value Theorem. The word mean means average, usually. From a statistical point of view, at any rate, what you have in front of you is a graph of a situation where we have a runner who is running for 6 hours. And during that 6-hour time, covers a distance of 30 miles. Okay. Now, you may have looked at a lesson like this earlier where you studied the difference between average velocity and instantaneous velocity. And this parallels that particular lesson. So what we have drawn here is this curved line represents the distance the runner has gone at the end of each time period. So you see the runner at the end of 1 hour has gone almost 10 miles. At the end of 2 hours, the runner has gone slightly less than 15 hours. So the runner's not running at the same pace the whole way, as you can see. Okay. Now, if this runner, the average velocity, this runner went 30 miles in 6 hours. So the average velocity of the runner, or speed of the runner, is 30 divided by 6, or 5 miles per hour. Well, that happens to be the slope of the line joining the starting point A with the finishing point B. The slope of this line is 30 divided 30, as you see, divided by 6. Now remember, this is just a rough, crude graph here. But so the line connecting that line right there, the slope of that line is the average velocity. Now, anywhere along here, if we drew a tangent to the curve, this is the velocity curve, speed curve, that would give you the speed the runner is going at that particular instance. Okay. Now, what does the mean value theorem say? Well, basically, if this runner ran at an average of 5 miles per hour, somewhere along the way, it would seem to reason that he was running at that some instance 5 miles per hour. Now we can look at the graph, and basically what that says is if this is the straight line represents 5 miles per hour, then any tangent to the graph that's parallel to this means at that instant the runner was going 5 miles per hour. And that basically, in a nutshell, is what the mean value theorem is all about. Okay? But we need to talk about it a little more mathematically. So, paraphrase, if you draw a graph and you draw a straight line connecting the initial point with the ending point, then somewhere on the graph there must be at least one time that the tangent to the graph is parallel to the secant line. The secant line is the line connecting the endpoints there. So here we have before us such a situation. I have a graph. Again, it's just a freehand graph. Okay? And I draw a line, straight line, connecting A to B. Then this mean value theorem says at least once along the path of this graph, the tangent line and the secant line must have the same slope, or they must be parallel to each other. Now, in this particular graph, as we've drawn it, there are 3 occasions where that happens. Okay? And that's basically what we're saying there. Let's go to the next page. Let's look at this drawing. Okay? And let's connect, as we did before, the initial point A with the final point B. This is the line. This is the straight line. Now, where on this graph can I draw a tangent line that has the same slope as this? And the answer is nowhere. Nowhere. So this means, does this mean that we found a counterexample? In other words, we found a situation where the mean value theorem doesn't work? In other words, we said back here that if you draw a curve and you connect the endpoints, at least once there is a line parallel, tangent line that's parallel to the secant line. And have we found a situation that that's not true? And the answer is no. What's wrong with this graph? What's wrong then? It has a sharp point here. And remember, something is not differentiable at the sharp point. Now, be careful. We're not saying that if it has a sharp point, it doesn't, you can't find a tangent line. What we're saying is if it has a sharp point, we don't guarantee that you can find a tangent line. I'll be back to the previous graph. What if I made a sharp corner point right here? Pointer right here. Well, that wouldn't interfere with my finding the tangent line. In other words, because the sharp point is not at the point where the tangent lines would be, maybe. So that's what we're saying here. Just because you see a sharp point doesn't mean you can't find a tangent line. But if you have a sharp point, we cannot guarantee that you're going to be able to find a tangent line. That's all we're saying there. So it looks like we need to modify and say, if you draw a graph with no sharp points, we can guarantee that somewhere along the way, the tangent line is at least one tangent line that has the same slope as the secant line. And that's true. Let's go to the next page. Again, I have a graph here. And here's my secant line. Starting point, terminal point. There is nowhere on this graph that the tangent line is going to be parallel to this line. So, have we found another? Is this an exception to the rule? And no, it's not. Now, what happens, this graph, if we go back forward a minute, this graph has a break in it. In other words, it's not continuous, okay? Now, come back here. Suppose I made a break in the graph here. I could still find the tangent lines, but we're not saying if it has a break in it that there are no tangent lines. What we're saying is if it's not continuous, we cannot guarantee a tangent line. So what we're going to do is now, based on what we've seen in these last two figures, one had a sharp point, one had a break, we're going to modify our definition to say if f is continuous, and it means no breaks. And if it's differentiable, that is no sharp points, then we guarantee that there is at least one C where the slope of the tangent line and the slope of the secant line are identical. Okay, and that, people, is what we call the mean value theorem. Okay. Now, let's look at example one. Example one. Let's suppose we give you a graph. Okay, just give you this graph from A to B, and we ask you to put an X anywhere that satisfies the mean value theorem. First of all, this graph has no breaks, no sharp points, so I need to be able to find at least one. So here's the way you go about finding that point. We're suggesting this with a straight edge. A straight edge might be a ruler. It might be the edge of your book or an index card or a plastic card. Connect these 2 points. and then take that ruler, that plastic card or whatever, and move it along the graph until the edge of the card or ruler is parallel to this line, and put an X there. So in other words, and then do it also, we find another one over here. So we have two of them. And you say, is that exact? No. Well, how would you know if we know what we're doing? Well, first of all, if you draw this line and then draw the dotted line, that kind of tells the person who's looking at it what's going on. But certainly if you put the X over here, where the pointer is, and you know, that is not where the X will be, or nor would the X be here. So it's going to be close, okay? Close. And that's what you call finding a solution to the mean value, justifying the mean value theorem graphically. And sometimes you have problems like that, and they're that easy. You say, well, you know, we've spent a couple of pages here talking about this. Yes, we have. It's pretty simple. Yes, it is. Okay. Now, what if you're not given the graph? What if you're not given the graph and you're only given the equation? Well, how would you go about it? Well, you might say, I get it in my calculator and graph it. Well, that might give you a close answer. But more than likely, you're going to have a problem where they want the exact numerical answer. So what are you going to be able to do? Well, first, let's remember, we're talking about slope. That's what is slope anyway? The slope of a straight line. Slope of a straight line is y2 minus y1 over x2 minus x1. Okay? So that's slope. Now we're taking 2 points from A to B. So if we have a function, then at A, the y-coordinate is f of A, and at B, the y-coordinate is f of B. So we can rewrite this y2 minus y1 is f of B minus f of A over B minus A. So here's another way of writing this. And so what we're basically saying in the mean value theorem, if you have a graph that's continuous from A to B, some function f of x, then you have at least one point where the slope is equal to f of B minus f of A over B minus A. Now, what is slope? What is this point? Well, we don't know what this point is. We do know slope. If you have f of x, what is slope? F prime of x. So what we want to do is find some point C, where the slope is equal to f of B minus f of A over B minus A, and we'll call that f prime of C. And we've talked a lot here. Let's go over and see, make it a little more formal, and I think it'll be clear to you. Here's what we're saying. If you have a function that's continuous and differentiable, then there's at least one C between A and B such that f of B, that's your endpoint, that's the y-coordinate of your endpoint, minus f of A, that's the y-coordinate of your starting point, over B, which is your endpoint, minus A, which is your starting point. There's some function value C, and this is the slope at C, it's f prime of C, they're equal to each other. So this is what you want to know, just this portion right here. This is the mean value theorem. This is what you'll use if you're given a function rather than a graph. So let's see how it works. Example 2, f of x is x squared minus 3x plus 5. And we're looking at it from 1 to 4. And we want to find all C that verify the mean value theorem between these 2 points. In other words, we want any answer between 1 and 4. If we get an answer bigger than 4, we're not going to use it. If we get an answer less than 1, we're not going to use it. Only answers that are between 1 and 4. Okay. So what do we need? Well, this is my A, 1. And this is my B, 4. And f of A is going to be, means f of 1. So it means take this function and put a 1 everywhere there's an x. And when we do, we get 3. And then f of b is 4, says take this function and everywhere there's x, put a 4 and do the arithmetic and get an answer. We get it as 9. Okay? So we have a, we have b, we have f of a, we have f of b. We need f prime of c. Well, f prime of x is the derivative of this thing, which is 2x minus 3. So f prime of c is 2c minus 3. Now we simply plug in to our formula here. In the place of f prime of c, we're going to put 2c minus 3. In the place of f of b, we're going to put 9. In the place of f of a, we're going to put 3. In the place of b, we're going to put 4. And in the place of a, put a 1. And now let's do the arithmetic. When you do, you get 2c minus 3 is 2. So 2c, when you bring the 3 over, is 5. So 5 halves, or 2.5, is our answer. Is it between 1 and 4? Yes, it is. So we pretty much feel confident about that. If you want to check yourself out, graph, this is just an a suggestion we're making to you so you get a nice graph. Go to your graphing tool, usually a calculator, and set your window between from 1 to 4, and so that, and set your window so that it's x minimum is 1, x maximum is 4, y minimum is 3, and y maximum is 9. And I think you'll see that that's just to check yourself out. I wouldn't say do this. We're not even suggesting you do this, but if you're curious on what it looks like, you can kind of check yourself out there on these. And let's go to example 3. F of x is x cubed minus 2x. Okay, and we have x is between 2 and -2. Find all the c that satisfy the mean value theorem. By the way, this function is continuous, and when we take the derivative, we see that it is differentiable. So we should find, and all we want are answers that are between -2 and 2. Okay, we will not accept anything that's not between -2 and 2. Okay, between, not from -2 to 2, but between -2 and 2. So now, a is -2. Now, b is +2. Now, f of a means put -2 into the function and do the arithmetic, and we get -4. And f of b means put +2 into the function. We get an answer that's +4. The derivative of this is 3x squared minus 2. So f prime of c is 3c squared minus 2. Now plug into your formula. What formula are we talking about? This one right here, back here. Plug into that. And when we do, we get f prime of c is equal to f of b, which is 4, minus f of a, which is -4 over b, which is 2, minus a, which is -2. And so, of course, this is going to be 4 minus -4. 4 plus 4 is 8. This is 2 minus -2, which is 4. So 8 divided by 4 gives us a 2. And then with it, we have this, we bring this over, and then we divide by, and then we take the square root, and we get a plus or minus 2 over the square root of 3, or plus or minus 2 square root of 3 over 3. At any rate, these numbers are between -2 and 2, so we don't have to discard them. Now, we don't have a problem here where you have to throw out, so you do need to check that out. If you get an answer that's beyond the equal to or beyond the endpoints, then you must discard that answer. But if the graph is continuous between these 2 points and differentiable, you should find at least one. If not, something's wrong. So this more or less concludes this lesson. This mean value theorem is very important for proving other theorems, and that's why we take the time to do this. But it also supports something that we learned earlier about the relationship between average velocity and instantaneous velocity. So we finished with this lesson.